Welcome to the Deep Dive. Today we're going to be taking a deep dive into the fascinating and often perplexing world of quantum mechanics.
Right.
Specifically, the Copenhagen interpretation and its philosophical implications.
Yeah.
And, it's a subject that's challenged physicists and philosophers alike for nearly a century.
It has.
So, to guide us through this quantum fog, we have our expert.
Absolutely. I'm happy to be here.
Ready to unravel some mysteries?
Always ready.
So, from what I understand, the Copenhagen interpretation isn't really a single unified theory.
Right.
It's more like a collection of ideas and principles.
That's true.
Developed by Niels Bohr and his colleagues in the 1920s.
Yeah, it's named after the city where a lot of this groundbreaking work took place.
Oh, wow.
Yeah. Copenhagen. And the interpretation isn't really a rigid set of rules. It's more like a framework for thinking about quantum mechanics and what it means.
I see.
Yeah.
So before we get lost in the weeds,
Okay.
can we rewind a bit and talk about what led to this revolution in physics? I mean, before quantum mechanics, there was classical physics,
Right.
which seemed to explain the world pretty well, right?
Yo, well, yes and no.
Okay.
Classical physics, as developed by, giants like Newton and Maxwell,
Right.
worked really well for describing the motion of planets, the behavior of light,
Yeah.
pretty much everything we could observe at the macroscopic level.
Okay.
But then as scientists started probing the world of atoms and subatomic particles, cracks began to appear in that classical facade.
Yeah, I remember reading about those early discoveries that shook the foundations of classical physics.
Oh, yeah.
Planck's idea of quantized energy.
Yes.
Einstein's explanation of the photoelectric effect.
Right.
And Rutherford's model of the atom. They all seem to point to a reality that was far stranger than anyone had imagined.
Definitely they were revolutionary.
Yeah.
Planck, in trying to explain the spectrum of black body radiation, he kind of stumbled upon this idea that energy isn't continuous,
Yeah, right.
but exists in these discrete packets or and this really challenged the classical notion of energy as like a smooth-flowing entity.
Okay.
Then you have Einstein in his explanation of the photoelectric effect,
Right.
showed that light, which was always thought to be a wave,
Yeah.
could also behave like a particle, a photon.
Wow.
Further blurring the lines between waves and particles.
And then Rutherford, with his gold foil experiment,
Yes.
blew apart the comfortable picture of the atom as a miniature solar system.
Right.
His experiments showed that most of the atom's mass was concentrated in a tiny, dense nucleus.
Yeah.
With electrons somehow orbiting around it.
And that's really where the problem started for classical physics, because according to classical electromagnetism, those orbiting electrons should be constantly radiating energy, which would cause them to spiral into the nucleus, in a fraction of a second.
Right.
And obviously atoms don't do that, so something was clearly wrong.
So that's where Niels Bohr comes in, right?
Right.
With his model of the atom that incorporated these strange new quantum ideas.
Yeah. Bohr's model, while still rooted in this idea of electrons orbiting a nucleus, introduced a radical new concept, quantized energy levels.
Okay.
So electrons could only exist in specific orbits,
Right.
each corresponding to a distinct energy level, and they couldn't just be anywhere in between.
So it's like those electrons were confined to specific floors in an atomic building, and they couldn't just hang out in this stairwell.
That's a good analogy.
Okay.
But here's the thing. While Bohr's model addressed this issue of atoms collapsing, it introduced another layer of weirdness.
Okay.
These electrons didn't seem to move smoothly between orbits.
Right.
They just jumped
Yeah.
in a seemingly instantaneous and unpredictable way.
Okay, so we're already starting to see how quantum mechanics challenges our classical intuitions.
Yeah.
But let's talk more about these jumps and the whole idea of quantum probability.
Okay.
It seems like a central pillar of the Copenhagen interpretation.
It is one of the most radical departures, I think, from classical physics, is this notion that at the quantum level, things aren't deterministic, but probabilistic.
Right.
We can't predict with certainty when or where an electron will jump between energy levels.
Yeah.
We can only talk about the probability of it happening.
So it's not that we lack sufficient information to make precise predictions, but that the quantum world itself is inherently uncertain.
That's the heart of it.
Wow.
And it's a concept that even Einstein, who revolutionized physics with his theory of relativity, struggled to accept.
Yeah.
He famously said, God does not play dice with the universe.
Right.
But quantum mechanics seems to suggest otherwise.
Okay, so Bohr's model, despite its strangeness, was a step forward.
Yeah.
Right? But he also introduced this concept of the correspondence principle.
Yeah.
Which I admit I found a bit confusing.
Okay.
It seems to be about bridging the gap between the quantum world and the classical world.
Yeah, the correspondence principle is crucial for understanding how Bohr viewed this relationship between classical and quantum physics. He recognized that while quantum mechanics was necessary to describe the behavior of atoms and subatomic particles,
Right.
classical physics was still incredibly successful at describing the macroscopic world, the world of everyday objects and experiences.
So he wasn't saying that classical physics was wrong,
Right.
just that it had its limits.
Exactly.
Okay.
The correspondence principle essentially states that quantum mechanics should, in a sense, converge with classical physics
Okay.
at larger scales where quantum effects become negligible.
Okay.
Think of it this way. A single water molecule behaves very differently from a glass of water.
Right.
But when you have trillions upon trillions of water molecules together,
Right.
their collective behavior starts to look like that smooth, continuous flow we associate with water in the macroscopic world.
Okay, so the correspondence principle is like a bridge between these two seemingly disparate realms of physics.
Yeah.
But how does this principle connect to the philosophical aspects of the Copenhagen interpretation? You mentioned earlier that it requires us to rethink some of our basic assumptions about reality.
It has profound implications for how we understand the relationship between the microscopic and macroscopic worlds.
Okay.
From a philosophical perspective, it suggests that the world we experience at the macroscopic level isn't necessarily a direct reflection of the underlying quantum reality.
That's a pretty mind-blowing idea.
It is.
Are you saying that the world we see and interact with is just an emergent property
It's a possibility.
of a much weirder, more probabilistic reality at the quantum level?
It certainly is.
Wow.
The correspondence principle doesn't tell us exactly how this emergence happens.
Right.
But it highlights the limitations of our classical intuitions when we try to understand the quantum realm.
Okay.
It suggests that that smooth, deterministic world that we experience is, in a sense, an approximation.
Yeah.
A simplification of a more complex reality operating at a deeper level.
That definitely challenges our traditional philosophical views
It does.
of a unified and objective reality. It seems like quantum mechanics is forcing us to question the very nature of what's real and how we perceive it.
Precisely. And this questioning leads us to another cornerstone of the Copenhagen interpretation.
Okay.
A concept that's both elegant and incredibly challenging.
Okay.
Complementarity.
All right, let's dive into that.
Okay.
From what I've read, complementarity seems to be about embracing the seeming paradoxes that arise in quantum mechanics, like the wave-particle duality of light.
Right. Complementarity is Bohr's attempt to reconcile the fact that certain descriptions of quantum phenomena, though seemingly contradictory, are both necessary for a complete understanding.
I see.
It's not about saying that one description is true and the other is false, but rather that they are complementary aspects of the same reality.
So it's like saying that depending on how you look at it, an electron can be both a wave and a particle. But you can't observe both aspects simultaneously.
That's a simplified way of putting it, but it captures the essence of complementarity.
Okay.
What Bohr argued was that certain properties, like wave-like behavior and particle-like behavior, are mutually exclusive, yet both necessary to understand the full nature of quantum systems.
So the act of observation.
Yes.
The way we choose to measure or interact with a quantum system plays a role in determining which aspect of reality manifests itself.
Exactly. And this brings us to one of the most controversial aspects, I think, of the Copenhagen interpretation.
Okay.
The role of the observer.
Yeah.
Bohr argued that the observer and the observed aren't separate independent entities, but rather part of a single interconnected phenomenon.
That sounds almost mystical.
Yeah.
Are we saying that our consciousness somehow influences the outcome of a quantum experiment?
Not quite. It's not about consciousness in the mystical sense, but about the fact that the act of observation, the choice of measurement apparatus, inevitably influences the system being observed. It's like saying that you can't measure the speed of a car without affecting its motion in some way.
So it's not that we're creating reality with our minds. But that the act of observation, the way we choose to probe the quantum world, defines the reality we observe.
That's a good way of putting it.
Okay.
Bohr was very careful to distinguish between subjectivity and the objective reality of the quantum world.
Yeah.
He argued that while the choice of measurement influences what we observe, the underlying quantum reality exists independently of our minds.
Okay, that makes sense.
Yeah.
But if the choice of measurement defines what we observe, does that mean there's no such thing as objective properties in the quantum world? Are things like position and momentum just illusions?
That's a question that's led to much debate and different interpretations.
Okay.
Bohr himself seemed to suggest that classical concepts like position and momentum, while useful for describing our macroscopic experience, need to be reinterpreted in the context of quantum mechanics.
So it's not that these concepts are wrong, but that their meaning and applicability are limited by the nature of quantum phenomena.
Precisely.
This is a lot to absorb.
Yeah.
We've covered a lot of ground.
Yeah, we have.
The breakdown of classical physics, Bohr's model of the atom, the correspondence principle, quantum probability, and complementarity. It seems like every step we take into this quantum fog reveals more layers of complexity and mystery.
And we've only just begun.
Oh, boy.
There's much more to explore.
Okay.
Especially when it comes to the philosophical implications of the Copenhagen interpretation, the measurement problem, and the ongoing debate about what quantum mechanics tells us about the nature of reality.
Well, it's clear that we're in for quite a journey.
Yes.
Let's take a pause here and pick up the thread in our next deep dive session.
Sounds good.
I'm looking forward to it.
Me too.
Okay, so we're back and ready to plunge even deeper into those philosophical depths of the Copenhagen interpretation. We've talked about complementarity, the role of the observer, and how classical concepts kind of need to be reinterpreted in the quantum context.
They do.
But I think we really need to grapple with one of the most perplexing issues in quantum mechanics, what's often called the measurement problem.
Yes, the measurement problem is a real head-scratcher.
It is.
It gets at the heart of the question, how do we reconcile this probabilistic nature of the quantum world with the definite single outcomes that we observe when we make measurements?
Yeah, I've read that the Copenhagen interpretation is sometimes criticized for being vague or even evasive when it comes to explaining what actually happens during a measurement.
There's some truth to that criticism. Bohr and his colleagues didn't offer a precise mechanism for how the wave function, which describes the probabilities of different outcomes. Supposedly, it collapses into a single definite result when we make a measurement.
But didn't we talk earlier about how Bohr rejected this idea of wave function collapse?
We did.
If the wave function isn't a literal description of reality, how do we make sense of the fact that measurements always seem to produce a specific outcome?
That's the crux of the issue. Bohr's view, as we discussed, was that the wave function doesn't represent a real physical wave, but rather a mathematical tool for calculating probabilities. He argued that the process of measurement isn't about this mysterious collapse of this wave, but rather about the interaction between the quantum system and the measuring apparatus.
So the measuring apparatus plays a key role in defining the reality we observe.
Yes.
We talked about this earlier with the idea that the choice of measurement influences what we see. But how does this help us understand this measurement problem?
Okay, well, Bohr's point was that the measuring apparatus being a macroscopic object is necessarily described in classical terms. It has these definite properties like position, momentum, and energy that we can measure and observe directly. When this classical apparatus interacts with a quantum system, it forces the system to manifest one of its possible outcomes, which we then register as a measurement result.
But if, as some physicists argue, everything is ultimately quantum, including the measuring apparatus, wouldn't that mean that the apparatus should also be subject to superposition and uncertainty?
It would.
How can something that's itself in a blurry probabilistic state cause a quantum system to choose a definite outcome?
That's a very valid question. And it leads to some of the deeper philosophical debates about the foundations of quantum mechanics. Some physicists, often called quantum fundamentalists, argue that the quantum formalism should be taken literally, even when it comes to macroscopic objects.
So they're saying that my measuring device, my ruler, for example, could be in a superposition of different lengths at the same time.
That's the implication, though. Obviously, we don't observe rulers behaving that way in the
Right.
macroscopic world.
Right.
And this apparent conflict between the quantum formalism and our everyday experience is what fuels this measurement problem.
So how do these quantum fundamentalists try to explain this discrepancy?
Right.
If everything is quantum, how do we account for the emergence of classicality,
Right.
the definite world that we observe?
One approach is through the concept of decoherence,
Okay.
which we touched on earlier.
Right.
Decoherence proposes that the interaction between a quantum system and its environment,
Yeah.
which could include, air molecules, stray photons, even the measuring apparatus itself,
Right.
effectively disrupts those fragile superposition states,
Yeah.
making them incredibly difficult to maintain at the macroscopic level.
So it's like the environment is constantly measuring the system,
Yeah.
causing it to decohere, to settle into a definite state.
That's a good analogy.
Yeah.
The idea is that these interactions with the environment act like a constant bombardment of mini measurements,
Right.
destroying that coherence that allows for superposition,
Yeah.
leading to the emergence of classical behavior.
Okay, that makes sense. It's like a cosmic game of telephone,
Yeah.
where the quantum state gets distorted and muddled
Right.
as it passes through this noisy environment, eventually losing its coherence and becoming a single clear signal.
That's a creative way of putting it. And
Yeah.
decoherence does provide a plausible explanation
Yeah.
for why we don't observe macroscopic objects in superposition.
Okay.
But the question remains,
Yeah.
does it truly solve the measurement problem?
Right.
Does it explain why one specific outcome is selected from all the possibilities encoded in the wave function?
Right. It seems like decoherence explains why superpositions are difficult to maintain at larger scales.
Right.
But it doesn't tell us how one particular outcome wins out in the end.
Yeah.
It's like saying that a spinning coin, when tossed in a crowded room, will eventually land on one side or the other
Yeah.
due to collisions with air molecules and other objects.
Right.
But it doesn't explain why it lands on heads rather than tails.
That's a key point.
Yeah.
And many physicists and philosophers argue that decoherence, while important,
Right.
doesn't provide a complete solution to this measurement problem.
Right.
It pushes the question back a step, but it doesn't fully answer it.
So where does that leave Bohr and the Copenhagen interpretation?
Right.
What was his stance on this issue of outcome selection?
Well, Bohr's position on the measurement problem is subtle.
Okay.
And as with many aspects of his thinking open to interpretation,
Right.
he emphasized the role of the measuring apparatus
Yep.
and the necessity of using classical concepts to describe measurement outcomes.
We've talked about that, how he argued that classical concepts are essential for communication and understanding,
Yes.
but that they don't necessarily reflect this underlying quantum reality.
Good.
But how does this relate to this question of outcome selection?
Well, Bohr seemed to suggest that the very act of measurement,
Uh-huh.
the interaction between the quantum system and the classical apparatus,
Right.
is what forces the system to manifest a specific outcome.
Okay.
It's not that the system chooses an outcome in any conscious or deterministic sense,
Okay.
but rather that the interaction with the apparatus defines the context in which a particular outcome becomes actualized.
So are we saying that the outcome wasn't predetermined,
Right.
but that it emerges from the specific conditions of the measurement itself?
That's one way to understand Bohr's perspective.
Okay.
He focused on the epistemological aspects of the measurement problem,
Right.
emphasizing, what we can know and
Uh-huh.
how we can describe the outcomes of experiments,
Yeah.
rather than trying to provide some metaphysical account of what's really happening at the quantum level.
It sounds like he was kind of sidestepping the ontological question
It does a bit.
of what constitutes reality in favor of a more pragmatic approach focused on what we can observe and measure.
That's a fair assessment.
Yeah.
Some critics argue that this is a weakness of the Copenhagen interpretation,
Okay.
that it avoids these deeper philosophical questions about the nature of reality.
Right.
Others see it as a strength,
Okay.
a recognition that our classical language and concepts are not well suited
Right.
to describing the quantum realm.
It seems like Bohr was acknowledging the limitations of our descriptive tools
He
while
was...
still affirming the reality of the quantum world.
Exactly. He wasn't denying the existence of a quantum reality,
Okay.
but he was careful about the claims he made about its nature.
Right.
He argued that our understanding is always going to be constrained by the tools we use to probe the quantum world,
Yeah.
by the experimental arrangements we create, and by the language we use to describe our observations.
So for Bohr, the focus was on understanding the conditions under which we can make meaningful statements about the quantum world. rather than trying to construct a complete metaphysical picture of reality.
That's a good summary.
Okay.
He shifted the conversation from a search for this hidden classical-like reality, underlying quantum phenomena, to a focus on the limitations of our observational and descriptive tools.
I see.
He reminded us that the act of observation itself plays a crucial role in shaping the reality we perceive, but it doesn't create that reality.
This is quite a departure from the classical view.
It is.
Of a world that exists independently of our observations.
Yeah.
It's like saying that the universe doesn't come with a pre-written script, but rather that the story unfolds as we interact with it.
That's a good analogy.
Yeah.
Bohr's insights have had a profound impact not just on physics, but also on epistemology, the study of knowledge.
Yeah.
They force us to question the very nature of observation and objectivity, to recognize the limitations of our classical worldview when trying to grasp the complexities of the quantum realm.
So even though the Copenhagen interpretation doesn't offer a definitive answer to this measurement problem, it provides a framework for thinking about it. A framework that emphasizes the context dependence of measurement and the essential role of classical concepts in describing the quantum world.
Exactly. It's a framework that has guided generations of physicists and philosophers in their quest to understand the quantum world and our place within it.
And that quest, as we've seen, is full of twists and turns.
Yes, it is.
And unexpected discoveries. But before we lose ourselves in the quantum maze, maybe we should pause here and take a step back.
Okay.
We've delved deep into this measurement problem and its philosophical implications.
We have.
But there's still much more to explore.
There is.
Yeah, the Copenhagen interpretation, with its emphasis on complementarity and the role of the observer, opens up this whole new way of thinking.
It does.
About the relationship between ourselves and the universe we inhabit.
Yes.
And this way of thinking, as we'll see, has implications that extend far beyond the realm of physics. It does. We've been exploring the Copenhagen interpretation, and it's safe to say it's really challenged some of my core assumptions about reality.
Yeah.
You know, it's like peering through a fog and realizing that the world is much more nuanced than we often perceive it.
That's a great way to put it. The Copenhagen interpretation, it doesn't really offer easy answers.
Right.
But it does provide this new lens through which to view the quantum world, this world where certainty gives way to probability.
Yeah.
And the observer kind of becomes an integral part of the observed.
One of the things that's been kind of swirling in my mind is this. What does the Copenhagen interpretation actually tell us about the nature of reality itself?
Right.
Does it even attempt to answer that question?
Well, that's a question that has really sparked endless debate among physicists and philosophers.
Yeah.
The Copenhagen interpretation is often accused of being anti-realist.
Okay.
Meaning that it denies the existence of an objective reality independent of our observations.
Right.
But that's a simplification.
So it's not saying that the moon doesn't exist when no one is looking at it.
No, not at all.
Okay.
The Copenhagen interpretation acknowledges the existence of a quantum world.
Right.
This world that behaves in ways that often defy our classical intuitions.
Yeah.
But it's very cautious about the claims it makes about the nature of that world.
So it's more about setting limits on what we can meaningfully say about reality, given the constraints of quantum mechanics and the limitations of our own perception?
Precisely. It's a stance of epistemic humility, I would say.
Right.
Recognizing that our classical concepts and everyday experiences, they don't fully equip us to grasp the complexities of the quantum realm.
But if it's not anti-realist, what is it saying?
Right.
Is there a way to kind of pin down its ontological commitments, its claims about what truly exists?
Well, this is where things get tricky.
Okay.
There are different interpretations of Bohr's own views.
Okay.
Some scholars argue that he was essentially a realist, believing in an objective quantum world, even if we can only access it through the filter of our classical concepts and experimental setups.
So they're saying that the quantum world is real, but it operates by a different set of rules than the classical world. We experience rules that our language and current concepts struggle to articulate.
That's a good way to put it.
Okay.
Others argue that Bohr was more of an instrumentalist.
Okay.
Focused on the predictive power of the quantum formalism, downplaying the significance of ontological questions.
But didn't we discuss how Bohr rejected the idea that the quantum formalism was just a predictive tool?
Right.
He believed it revealed something profound about the nature of quantum systems, even if it wasn't like a literal picture of reality.
Exactly, and that's what makes his position so fascinating and difficult to categorize.
Right.
He walked this fine line between realism and instrumentalism,
Yeah.
acknowledging the limits of our descriptive tools while affirming the reality of the quantum world.
It seems like trying to fit Bohr into a neat philosophical box misses the nuance of his thinking. Maybe the key is to kind of appreciate the subtlety and the open-ended nature of the questions that he was grappling with.
I think you're right. The Copenhagen interpretation, as we've seen, it's not like a rigid doctrine, but this dynamic and evolving set of ideas reflecting our ongoing efforts to reconcile our classical intuitions with the mind-boggling realities of the quantum world.
And this struggle, as we've seen in this deep dive, takes us to the very edge of what we thought we knew about the universe and ourselves.
It does.
It raises questions not just about physics, but also about the nature of knowledge observation and the limits of human understanding.
Right.
Yeah, the Copenhagen interpretation, with its emphasis on complementarity, the role of the observer, and this need for reinterpreted classical concepts, it offers a valuable framework for navigating these really deep waters.
It does.
It may not have all the answers.
Right.
But it's certainly provided a launching point for some really profound questions about the nature of reality and our relationship to it. This deep dive has been a real eye-opener. I feel like I've only scratched the surface of this fascinating subject.
Well, the journey of exploration and discovery, it's never truly over.
That's true.
Each new insight, each new question just opens up new pathways of understanding.
Well said. I want to thank you for guiding us through this complex and thought-provoking landscape.
You're welcome.
And to our listeners, we encourage you to continue exploring, questioning, and pushing the boundaries of your own understanding.
Yes.
The quantum world is filled with wonder and mystery, and who knows what awaits us as we delve even deeper into the fog.
The journey is just beginning.
Thanks for joining us on The Deep Dive.